And now we move to our next speaker, Mr. Georg Schett, who is going to talk to us about the next digital substations. So I think power is something we will most definitely need in the future, no matter what it's going to look like. We need to charge our things and power our things. And maybe we will import power on boats in bottles from Africa.
Yeah,
bottle sunshine.
Robots need power as well.
Yes, lots of power. So, please, thank you.
Okay, thank you very much, Henrik. Digital substation. That's an area where I'm not so sure that many of us or of you already really know what a substation is. Therefore, I will quickly explain what is really a substation. And because normally they are very well hidden, we cannot see them all over the place. But as per this picture, you can see there, substations are today still huge, need a lot of space, bulky. Some people think that they are just standing there making noise. And I will try to convince you that there is a lot of technology developments in substation. What you see here is an air-insulated substation, big one, 420 kV. And here is a gas-insulated switchgear. This is in a dam. I think it's even Itaipu, it's in Brazil. It's 900 meters long. So you need a bicycle if you want to repair it, you know. So this is substations today, but this will change. If you're looking into Estonia, I mean, substations, you have maybe 20 bigger substations. They are located in these nodes in the network. So you have transmission lines, and sometimes transmission lines meet. And at those meeting points, there is normally a substation. So if you're looking at all these lines you see all over the place, at the end, if you walk to the end, you will see a substation. So that is normally how a substation looks like. And if you're looking into the substation, what does a substation do at the end of the day? A substation interconnects lines. So you can switch on, switch off a line. Therefore, in a substation, you will have, for example, disconnecting circuit breakers or disconnecting switches. You can also earth or ground a line, that you can do some work on a line. Therefore, it has to be earthed. So there is some grounding equipment in substation. You are connecting lines having different voltages. For example, in Estonia, you have typically for a long-distance transmission, you have, I think, 320 kilovolts. And then regional, you have 220. Then it goes down to 110. And then you have distribution, 10 kilovolt, 20 kilovolt. And at the end of the day, you have 220 volts in your houses. And everywhere, there is a kind of a substation, because you need to connect. And how do you connect? You connect by means of transformers. And the transformers are these big animals you can see here. These are transformers. You need also to protect the substation, to protect lines, to protect transformers, because it might be that you have a power line, and then there is a lightning surge, thunderstorm. The lightning surge hits a line, and then you have a short circuit, and you need to very, very quickly interrupt the short circuit, because otherwise you will destroy a lot. You will destroy generators, transformers, breakers, and so on. And therefore, in a substation, you have also breakers. These are these other big animals you see there. And then you have measuring equipment. You want to measure currents, because if there is a short circuit, how do you detect it? By measuring currents or measuring voltages, or both. You want to get money for the power, so therefore you have also to measure very, very precisely current and voltages for metering. So there is a lot of equipment, and since this is high voltage, all this equipment needs a lot of space. It's bulky. And this is exactly what we will change now in the next 15 years. Because there are a bunch of new technologies now available, and that's what I want to talk about. So yes, there is big shifts in power, and there is also big shifts in automation, as we just heard. In automation, for example, more and more is connected. So at the end of the day, probably the wash machine will be connected to the internet, or the fridge will be connected to the internet, God knows what. A lot of things. You yourself will be connected for measuring your health. All this connection is happening now, and why should it not happen also in the power systems? In the power system, we have huge changes right now going on. The major shift you see in the power is that you do not anymore have these bulky power generation plants, which can be very well controlled, very accurately controlled. but you have intermittent renewable energy sources which are feeding in power into the grid. So this intermittency, that means you cannot control anymore so well. The loads you can already not control, because who knows when you switch on or off your lights at home? You know more or less, you have statistics. But at the end of the day, very helpful was in the past, power generation could be controlled very accurately to keep the balance between needs and between the sources and the loads. On this slide you see now, for example, and this is the major change we see, this intermittent power. This is a picture from E.ON showing what happens with wind power here. And of course, if you have these kind of sources coming more and more into the grid, you can imagine yourself how much efforts you will need in the future to be able to keep the grid stable, to avoid blackouts, keep the whole system running. Because also on the load side, you will see changes. For example, we will have e-mobility in the future. So cars will move from the night. They will have charging stations during the night at your home. And all these cars during the day, they will be plugged in into at your offices. So the loads will completely change. And on top of it, you have also so-called prosumers, meaning that a lot of people at home will install their photovoltaics. So there will not be any more decentralized power generation plants as today. There will be big wind farms, maybe even offshore. Good space here to do that in the Baltics. But there will also be power generation at the load centers, in the houses, on the rooftops. That has happened in Germany already. I mean, Germany today, a couple of years ago, people said that if in Europe one day a country has more than 5% power generation coming from renewable, it will be a total blackout. Today we have in Germany more than 20%. They target 40%, even 50%. Today people think 50% is possible. That will happen. And in some countries in Europe, for example in Denmark, some days of the year they have already more than 100% renewable power generation. Why do I say all that? Because if that happens, you will need a much more flexible grid. Everything has to be more flexible. Look, today, this is what you have. You still have a lot of bulk power generation. This is conventional, the gray and red and blue, conventional generation. But you see that the peak loads already today are managed by solar and wind. So the peak are shaved away. And this is what we have today, and this is what is planned by 2020. And this is not that long ago, a long time anymore. You see that the conventional power generation needs to be much, much more flexible, so we will see much more interconnections. But overall, what you will see in the power grids is that you need much, much more automation. Today, for example, a utility colleague in Germany told me that, look, a couple of years ago, we had 2 connections. We had one winter arrangement in our grid and one summer arrangement in our grid. Today, we have to switch up to 20, 30 times a day, and it's increasing. Why? Because of this intermittent power generation. They have to optimize the grid every day, every hour, in the future, every minute. Meaning that you will need much, much more automation in the grid than compared to today. Today, a lot is still done by phone. I need a little bit more power. Tomorrow, no way. That will not work anymore. Therefore, you need much more automation in the grid, but it means also, if you want to automate, you need to measure. And there is where digital substations come in. Another change as well, which has happened in the last years. Look, this is the conventional power system we have been used to in the last, let's say, 50, 60, 100 years. It was very simple. You had a power generation, and you had lines, and then you had the load. You had your homes. So it was very simple. Power was flowing from the generation to the loads, and revenues or money was flowing basically the other direction, from your pockets to the generation company. That was a simple setup, but that has now changed. That is the other change, which has been so important. We call this unbundling. This is a process which has already been starting 20 years ago, and it is now really starting to be accelerating extremely. And that means that still you have the power generation flowing in one direction. However, not anymore only in one direction. Now you have it also coming from renewable generation. You have it coming from distribution networks. So it has changed a little bit. But what is also changing extremely is that the revenue flows goes in the other direction. So you have much, much more players today in the market, in the power market, than only a couple of years ago. That is a tremendous change because that means also that all these new players in the market, they want to drive their businesses efficiently. Driving a business efficiently today can be done only if you have connections. You have connections maybe to internet, but you have connections to systems which allow you to drive your business much, much more efficiently. For example, you will see that all these new players in the market, they need to have access to data coming from sensors in the grid. These sensors could, for example, be current and voltage sensors. These sensors could be monitoring devices, which is monitoring the performance of, for example, power plants, or of distributed generation, or of transformers, or breakers. So we need to change the data which are coming from all these devices. And digital substations are key features, are key components to deliver these data. So the digital substation is a node in the network, and it is only with digital substation that we will manage the change from today's slow-moving, easy-to-control systems to a very nervous system we will have tomorrow. Digital substation is a key there. Digital substation includes, for example, more communication. It includes more measurement. It supports grid stability. It supports the efficient management of assets. So utilities, bigger utilities have, for example, thousands of transformers. How do they want to efficiently manage the services, the maintenance of all these transformers, if there is not a system behind helping them to do that? They will go for a renewable integration. A digital substation can support renewable integration. It can also, for example, thanks to environmental monitoring, measuring the temperature, you can suddenly overload transmission lines, for example. If you have an emergency situation, today it happens that the transmission line is just automatically switched off. So you lose the power, you may even black out a whole region. In the future, you will have sensors. They will really measure the temperature of the line, they will measure the temperature of the transformers, and they will conclude how much you could maybe overload these systems in case of emergency in order not to black out. So this is coming now. And this is really what you see in digital substations. Now, digital substation with so many more functions as you see here, will it be much more expensive? No. Why? Because there are new technologies. And this is just a glimpse of the new technologies we are talking about. An important part of a substation is, for example, the conventional current and voltage measurement transformers. These are those parts of equipment you need, for example, to measure currents in order to detect if there is a short circuit or an overcurrent or a failure. So these components are very expensive and very bulky. On the other side, you see here also voltage measurement transformers. These transformers are now replaced by tiny, small little sensors. These sensors are very accurate, very precise, and they are integrated in equipment. Before they were separate, and they needed a lot of space. Today they can be integrated, and I will show you how this is done. We have completely new technologies, for example, for communication. Today, you are able to very, very accurately sample voltage and current, analog current and voltages, sample it, digitize it, and make it available to anybody in the substation who needs it, be it a control, be it a protection, or be it a metering device. And you can even make these very, very accurate signals, digital signals, available in the grid, wherever it is needed. So this is a transformation of how the architecture of the future substation is looking like. What does it mean also? It means not only that there is clever new technologies, there is also visible impact. And this is just a picture showing you a conventional, traditional air-insulated substation, I said it needs a lot of space, it is bulky, and the digital substation, also air insulated, will use less than 50% of the footprint. Meaning that you could place in the future substation in locations where today it is not possible, just because you do not have the space. That also means that you will be able to change the topology of the network, to adapt the network to new opportunities, to new features which you do not have today. So these substations then really provide all the necessary data. Now I would like to go a little bit further and explain to you what are then the technologies which make a conventional substation digital. That is the topic. And here, what you see here is just a sketch, a model, a simple model of a substation. What you see here is, first of all, in this small little house here, you have control on protection equipment. This is high-performance electronics, really high-performance electronics. You have it protected in the control and protection room here. And then you have, for example, breakers. Sorry for the two screens. You have breakers here. Breakers are extremely important safety devices. If there is a short circuit, a breaker has to interrupt the short circuit within 10, 20, 30 milliseconds very quickly. And it has to work. There is no option. It has to work. So we have to understand, is the breaker okay or not? We have to monitor it. Yeah? What you also see here is transformers, these big animals. Transformers will get more intelligent in the future. And the most important part you see on this picture is this yellow stripe here. This yellow stripe is connecting control and protection electronics. Control and protection electronics is the electronic which is needed, for example, to detect a short circuit or an overload or whatever else. This yellow stripe is connecting the protection equipment to the primary equipment. Primary equipment for me is breaker, I mean the big things, you know, the transformers, breakers, disconnecting switches, and so on. This is primary equipment. And this yellow stripe, these today in the conventional technologies are still thousands of point-to-point wires. You can imagine in such a substation, I mean, you have more than 10,000 individual wires to, for example, connect from a tripping output of a protection device to a breaker. A lot of things have to be redundant, and you can imagine how difficult the engineering of such a substation is at the end of the day with all these things. And that is the first thing which will be changing now. A digital substation will substitute these conventional copper wires, these tons, 100-meter-long copper wires, for the individual point-to-point connection, signaling wires, as we call it as well, by means of a few fiber optic communication buses. This is this yellow stripe. So this is one of the headache. We can reduce, with digital substation, we can reduce up to 80% of the wiring in a substation by few fiber optic communication buses. Why only 80%? Because you will have a lot of electronics. And these electronics need power, like the robots. And therefore, you still will have a couple of copper wires to feed the power to these electronics, but the rest, all the signaling, will be made with optics, optical fiber. So this is the first thing which will happen. Just to show you here, if you are going today into a substation, this is normally what you will see. What you see here is primary equipment. This is a switchgear. This is, for example, a GIS, gas-insulated switchgear. Then you have a local control cubicle directly at, for marshalling. Then you have control and protection. And then you have, on the substation level, you have the station level, HMI, and all these things. And all these components are interconnected by all these thousands of point-to-point wires. This is old technologies, but this is still what today is installed. What utilities buy today is what you see in the middle. We call it modern. Utilities have always, in the last 20 years, have already agreed to change the whole station level up to the control and protection and replace all the wiring on the station level by means of fiber optic communication buses. That has been happening in the last 15 years, 20 years, and today a utility is close to always buys what we call a modern substation. What you still see here is that there is a wiring between the control and protection cubicle. By the way, the control and protection cubicles, these panels start to be much, much smaller because also on the control and protection computers, there is a lot of progress and there is a lot of functions which have been integrated. So where in the past you needed a lot of different devices, today you need one device which can do everything. Therefore, also the control and protection rooms have been shrinking already a lot, but still here you see a lot of point-to-point connections. There is still a lot of wiring, and these are exactly the longest wires in an air-insulated substation. We are talking about several hundred meters of cable. And this is now what is happening. This is now the future. This has started today, that we change also this equipment, the connection between control and protection. You remember the control and protection house I was showing to you and this yellow stripe? This is now this process bus. We call this process bus. And the process bus has features which are new and which, why did we do that only now? For two reasons. First of all, you needed to have the technology which is extremely precise because we need to have a very, very precise time stamping. One, so precision is one thing, and speed is another thing. And the second thing which was important is that it needs to be standardized. Our customers do not want to be trapped with one and only one supplier. They want to have the choice to choose amongst different suppliers, and therefore all these red stripes here, these buses have been standardized. This standard is called IEC 61850, and the process bus has an amendment -9-2. The process bus is able to transmit not only values as we can see here on the station level. On the station level, what you normally have is a kind of a client-server transmission of data, so there is not that high requirement for precision and for timestamping. So it is transfer protocols, very easy stuff. But then you have also on the station more and more what we call GUIs. So for those who are engineers, they know that you have to, for example, have some interbay interlocking. Also for this interlocking has to be extremely precise and accurate. And also these functions today are performed by means of a station bus. And what is now coming new with the process bus, this red stripe down here, is that it can also transmit very accurately so-called sampled values. So with 4,000 hertz, all these current and voltage sensors which are in the substations are measured, 4 kilohertz, in the future even more. And these sampled values are then exchanged between the primary equipment through merging units and control and protection. So these are the changes here, and this is just to illustrate why this happens. You remember I told you the many connections, the many wires between control and protection and primary equipment. Here is a transformer, breaker, and so on. So thousands of wires, and this is how it looks like in reality. This is just for a medium voltage substation. Look at the medium voltage substation here. That is how the conventional connection bay by bay look like. So these are the thousands of wires I was talking about. It's a lot. And if you're looking into one of these cubicles here with control and protection, I mean, it's a mess of cabling. It's a mess of cabling. You can imagine what happens if you have to repair something or to basically change, service it. It's a nightmare. That will all completely disappear in the coming years. The technology starts now to be ready, and we have started to go there. Now, if you have now these fiber optic buses, you do not need anymore these bulky current and voltage transformers, measurement transformers. You can replace them by sensors, because with these buses, you can go with electronics very close to the current and voltage measurement devices. So you do not need any more power output for these measurement devices. Today, the output is a couple of amps and around about 100 volts to measure current and voltage. That will not be needed anymore. You can then basically measure on millivolts or milliamps, microamps. So this is a completely different level. But then you cannot transport anymore these measurement signals a couple of 100 meters through a substation. Then you have to digitize it immediately at the sensor, meaning that at the sensor you will also have basically a piece of electronics. And this is exactly what you see here. This is an example of a sensor for gas-insulated switchgear, and this is an example for a current sensor, an optical current sensor for air-insulated switchgear. Here you see two pieces of electronics directly at the sensor. And directly at the sensor, this electronic is then basically converting the analog signal, the low voltage analog signal, to a digital signal. High precision, very high speed, 4 kilohertz. What does it do to the primary equipment now? Once you have these sensors, you can integrate the sensors into the primary equipment much, much easier. This is an example of gas insulation, a gas-insulated switchgear, where you see here a current and voltage sensor, here a current and voltage sensor. And in air-insulated here, you see an optical sensor, and this optical sensor basically works based on a polarized light beam, and the polarization angle of light is changed in function of the magnetic field. This is a quantum physics effect, which many people understand, not me, but it works. It is extremely precise, but the sensor can now be integrated into a breaker. So you do not need anymore a separate device to measure current and voltage. You can integrate all these functions into one piece of equipment. And this is one of the reasons, as I said before, that the substation will shrink. In case of a gas-insulated switchgear, for those who really want to know how it works there, this is now, you remember this gas-insulated switchgear I was showing? This is now just such a sensor. Here in the sensor, this is the conductor. The middle part is the conductor, high voltage. Here you have ground potential. In between you have an insulation gas. So high voltage, high current, ground potential, you can touch it. And in case of GIS, we put electronics directly at the sensor, and then you have two Rogowski coils and two capacitive rings who are sensing the current and the voltage. Extremely precise. Today, a conventional current transformers, for those who are specialists know, they have a nonlinear characteristics, they have a hysteresis, and that means that for each and every type of measurement, you need to have a completely different core. So at the end of the day, measuring current in a conventional substation needs a lot of cores, needs a lot of engineering, has a lot of wires, and. With sensors, they are perfectly linear because they have no core. So there is no saturation. Therefore, they are linear, and therefore you need only one sensor for control, protection, and metering. So that completely changes also the way how you can engineer substations. Then, directly at the sensor, as was saying, there is electronics, so there is some sampling. So you see the output of the sensor is analog. With this analog signal, you go to this electronics, and in the electronics, you will have a sampler. So you transform the analog signal into a digital signal, and in the merging unit, you then collect these sampled signals and package it and put it on this bus, which is standardized IEC 61850-9-2. This is available. This is a technology which is now coming. And ABB has been basically pioneering this technology. The first sensors have been developed close to 15 years ago. They are in service since then. And now, after so long time of testing, we have 300 of these sensors all over the world. After the time we have now tested it, and we have seen it's highly reliable, the electronic is reliable, we have decided now we go. We go publicly and we announce it, we launch it, and we want that our customers can take advantage of the advantages. Reduction of the footprint, I was talking about it, you can see it here. Air insulated, you integrate current and voltage measurement into the primary equipment, so you really shrink the size. This is an example in a GIS substation. You have here a voltage measurement transformer, conventional. This is a conventional current measurement transformer, and here you have all the control and protection cubicles. That will all disappear. So you will see that the current measurement is integrated into the combined sensor for current and voltage. and you will see that all these electronics can be integrated into the primary equipment. So for a conventional GIS here, with current measurement, voltage measurement, you will see that you will replace the measurement by sensors, and you see how much less space you will need in the future. And the equipment, I think, even looks nice. Look, you get rid of all the cabling. This is conventional. This is now modern. And you can then integrate control and protection very, very closely to the primary equipment. So that is what a digital substation is all about. Then you have monitoring and diagnostics, of course. Monitoring and diagnostics today is a big thing for utilities. They do not know is the transformer okay or not. They have no clue. They do not know if the breaker is okay. Therefore, they regularly send people to watch, is it okay or not. So they have a whole plan, time-based, where they go and watch the equipment. Monitoring and diagnostics will be performed automatically in the future. You will even be able to overlook your entire fleet. So from one place in Estonia, you could really have the whole overview of all your transformers in the grid. Distribution, power, and high voltage. So this is happening right now. And this is maybe a summary. So we will really see that all these devices are completely connected, integrated. And this is exactly not the case today. So there will be a lot of communication. And at the end of the day, what are the advantages? We can reduce the wiring 80%. We have a standard communication. The standard is IEC 61850-9-2. It's an IEC one. Then we have a footprint reduction of up to 50%, as I was explaining to you. So the size will shrink. And we will have operational expenditure reduction of up to 50%, because you can much, much more efficiently service and monitor your equipment. So this is digital substation. This is just a picture you should remember when you go home. On the left side, you see all the mess with the wiring. This is conventional with the primary equipment here, breakers. And you see control and protection. You see all the wiring. And that will be replaced by these red stripes here, which is then the fiber optic communication we were talking about. And you will see how the substation footprint will shrink. So this is the picture you have to remember when you go home. I have been talking all the time about high voltage. I have a bad conscience now because the biggest volume is probably in the medium voltage. Yes, what we have now shown on the high voltage is happening also on the medium voltage. You see here a medium voltage with sensors integrated. The cubicle is empty. And what you can also do, you can replace you can make a digital substation in a conventional substation without changing the primary equipment. I stop here. Fine. Thank you.
Thank you. I hope we have questions. Yes?
Are there any working prototypes of the digital substation, and when do you plan to make it, or why weren't any pictures of the working station of it?
Thank you for the question. That would have been my next slide. So, of course, we do not talk about things which do not really exist. We have more than 300 high voltage sensors for current and voltage measurement installed worldwide. The biggest bulk is in Australia. We have 5 substations which are working before 2000. We have tested it for more than 10 years, and since 2010, they are in operation with the process bus standard I was talking about to you. So we have more than 10 years of experience. I think we are the company who has the longest experience. We have been basically thought leader in this development. So we have 300 sensors for high voltage. We have a couple of other installations. In Sweden is one with the optic sensor. We have just now inaugurated a station in China. With 9 bays, 420 kilovolt. It was a tough exercise because they were extremely tough with the testing, our customers in China, SGCC. So this is technology which today works. And I'm standing here because I am personally now confident we can go. It is reliable and safe. Right?
None in Estonia.
Oh, please. Oh. That would be a pleasure.
Yes, I think so. Any more questions? So we have some time. Grid stability, quite important. What happens if we put these things in the grid?
Yeah, right. You know, grid stability is, for me, will be a key topic in the next 10 years. And in order to keep the grid stable, you need to know the status of the grid. And where can you better know the status of the grid than in a substation where you measure current and voltage? So what we will see in the future is that in digital substation, we will have phasor measurements. So we will measure the phase angle between current and voltages, and we will send this information to the grid. And in the grid command center, you will get all these measurements from your grid, and then you will see small angular differences between the individual voltages and currents. And that will be parameters you need to know to establish, to understand the status of the grid. So you will have real-time control of the status of the grid. Today it is already done, but today it is relatively slow. Here you will have a very fast, very responsive, very quick overview of the grid stability, and on top of it, because of monitoring and diagnostics, you will be able to overload your equipment in the emergency case. This is a very interesting topic, I can tell you, and especially for those working at universities, students, this is a key topic because there is a lot of technologies behind it. Right? Yeah. Okay?
So with the old technology, we know how it behaves. We know how long it lasts. It's been around for a long time. It's been tested. This new one, not so much. You know, my laptop just died the other day. With electronics, things happen.
Yeah, the problem is that you have a laptop, and maybe even a cheap laptop.
No, it's very expensive. It's very, very expensive, actually.
No, I mean, I was joking. Sorry. No, the point is that the electronics we are talking about here is, of course, not this type of laptop electronic. This is industrial electronics, high-level electronics. And we have measured, of course, what is the life expectation of this electronics during the last 15 years, where these things have been installed. And today, and by the way, all this electronics we have for control and protection is already electronics. And there we have a lot of experience during the last 25 years. So today, control and protection electronics typically has a life cycle of about 100 to 150 years, mean time between failures. This is what the standards, what investigations, SIGRE investigations show us. The electronics we have developed, and this is what you still have with digital, this is the same thing. But what is different is now that the electronics we put close to the process. This is electronics which is stressed by temperature cycles because sun, wind, snow, and so on. So the stresses are slightly different, and therefore this electronics had to be developed in a different way. It had to be adapted. And there are electronics where you can manage these things. And the mean time between failure is not only 100 years as for conventional, it is more than 300 years. This is based on our experience we have so far. So I consider this electronic as be very reliable, right? Okay.
And what's the life expectancy of current technology?
That's a good one now. I mean, the point is you have normally for the primary equipment, you know, transformers, breakers, and so on, they have a life experience of 30 to 40 years. Electronics, it's 15 to 20 years. But this is already like this for conventional electronics. And this has also an advantage, I mean, meaning that utilities normally every 15 to 20 years, they completely exchange the electronics. This is already happening today. But this whole process in the future will be much, much simpler because you will not anymore have this wiring. You will have fiber optics, and the speed of replacement will be massively better than what you have today. So this is, once during lifetime of primary, you will have to change the electronics. But this is the same as today, no change, right?
Okay. Do we have any more questions from the audience? I see no hands. Thank you, George. I will hand you a book also. Thank you.
Thank you.